Up until now, we've been focusing on the aspect of kinematics that's called forward kinematics. In forward kinematics, you are given the joint angles. The joint angles are things like theta 1, theta 2, d1, d2. And you're asked to find the location of the end effector. And once you've done that, you can use the location of the end effector, and specifically the homogeneous transformation matrix H can be used to find not only the location of the end effector, but also the location of a point from one frame to the next. Today, we're going to start talking about a different problem that's related called inverse kinematics. In inverse kinematics, you are given a desired location for the end effector. And you're asked to find the joint angles that result in that particular end effector location. Inverse kinematics ends up being much more useful to us as robotics engineers because typically this is the kind of a problem that we need to do with our robots. For example, we might know that we need the end effector, if it's, say, a gripper, to become located where an object is located that we want to pick up. In order to place the end effector in our desired location, we need to figure out what joint angles will place the end effector in that location. And that kind of a problem is inverse kinematics. Unfortunately, the inverse kinematics problem is also somewhat more difficult than the forward kinematics problem. In fact, the inverse kinematics problem is so difficult that we can only solve it if we make a couple of assumptions to begin with. Our first assumption is that only the first 3 joints of the robot manipulator determine the position of the end effector. And we're not particularly going to try and make those first 3 joints put the end effector at the right rotation. All we're going to do is try and get those first 3 joints to put the end effector in the correct position or the correct location. Our second assumption is that the second 3 joints of the manipulator determine the orientation or rotation of the end effector. And so, taken together, this results in another assumption, and that assumption is that the manipulator consists of exactly 6 joints. For the first 3 joints, we don't have to make any kind of assumption about what configuration those 3 joints are in, as long as they're in a configuration that gives us a range of motion or a workspace in 3 dimensions. However, we have to make another assumption yet about the second 3 joints, and that is we're going to assume that the second 3 joints make up a spherical wrist. And I'll be showing you more in the upcoming videos about what is a spherical wrist and how do we use that to determine the orientation of the end effector. For this video, I'm going to focus specifically on how we do the position part of the inverse kinematics problem. In the position part of the inverse kinematics problem, we're trying to find some equations. And we want equations that relate the joint variables as inputs to the x, y, and z location of the end effector. Now, finding these equations is sometimes easy and sometimes quite difficult, depending upon what type of manipulator you have. The good news is that once you've derived the equations, you can use those equations anytime you encounter a manipulator of that given type. For example, once you have the inverse kinematics equations that apply to a Cartesian manipulator, you can use those equations anytime you have to do a calculation for a Cartesian manipulator. You don't have to rederive them for every new manipulator you might encounter. In this video, I'm going to show you how to derive the inverse kinematics equations for one or two manipulators, and then I'm going to give you the equations for the rest of the manipulators. Here, I've shown the kinematic diagram for a Cartesian manipulator. On this diagram, I've already drawn in all of the axes and all of the variables that we'll need in order to derive the inverse kinematics equations. Let's start out by making sure that we know what it is that we're trying to find from this kinematic diagram. We want to find the joint angles D1, D2, and D3 that get the end effector into a position that we set. So, in other words, we want to find three equations. Our first equation will be the value of D1 as a function of x 4, 0. That's the position of the x position of frame 4 relative to frame 0, y 0, 4, and z 0, 4. And we can also have this equation be a function of my link lengths, which here are A1, A2, A3, and A4. We also want a second equation that will tell us the value of D2 as a function of the same things as D1, and a third equation that tells us D3. If we have these equations, then we can put these equations into our robot control program to command these three joints, which we have control over because we have motors on these three joints, in order to place the end effector in whatever location X, Y, Z we want it to be in. So how can we find these three equations for D1, D2, and D3? We will use the same process to derive these equations regardless of what type of manipulator we are looking at. And this process has two steps. One step, it doesn't particularly matter which order you do these two steps in, but one step is to look at the manipulator from the side view and write as many equations as you can from the side view, and then we'll turn the manipulator and we'll look at it from the top view. I'll show you what I mean for this Cartesian manipulator. First, we'll take a look at the manipulator from the side view. When I say that we're going to look at the manipulator from the side view, what I mean is that we're going to imagine that your eye, where you're going to look at it from, is going to be over here, and you're going to look in this direction. When you look in this direction at the manipulator, it will look something like this to you. I'm going to draw it down here in the side view. You'll see this same stick sticking out here, and you'll see x0 pointing to the right. I'll do this in the same colors as in the diagram. x0 will be pointing to the right, and z0 will be pointing up, but you won't be able to see y0 because y0 is pointing into the page from your point of view. You will then see a square here, and this square is this square, the back of this joint. The frame that you will see for frame 1 will have y1 pointing up, and it'll have x1 pointing to the left, but z1 will be invisible because it's pointing directly into the page or into the screen. Now, joint number 2 will be invisible to you looking from this point of view because joint number 2 is completely hidden behind joint number 1. I can, however, draw in some of the axes that you might see. You will be able to see Z2 pointing out to the right. And you'll be able to see Y2 pointing up. But X2 will be invisible. Finally, joint number 3 you will see positioned over here, connected with its link. And you will see parts of its frame. You'll see Y3 pointing to the right and Z3 pointing down. Finally, you'll see the link connecting to the end effector pointing down, along with portions of its frame, Y4 pointing to the right and Z4 pointing down. Now, I'm also going to label on this picture some of the variables that we can see in the picture. For example, we can see that this link length is A1, just as it's labeled up here in the diagram. And we know that the distance between here and here is equal to the link length A3 plus however much this joint variable has been extended, D2. And also we know that this distance right here is equal to A4, the length of this link, plus D3, however much this joint has been extended. Once I have this side view drawing, I can write some equations for the joint variables as a function of the end effector. I'm going to do that by using the geometry of this picture. One equation that I can write is representing the x position of the end effector. The x position of the end effector is right here. This is the x position of frame 4 in frame 0. What is this distance equal to in terms of my joint variables? Using the values that I've drawn on the distances in this drawing, we can see that x04 is equal to this distance up here, A3 plus D2. I can then change the order of this equation to write that D2 is equal to x04 minus A3. And that gives me one equation that expresses my joint variables in terms of the position of the end effector. There's one other equation that I can write from this diagram of the side view. Let's write this other equation. We can also write an equation for the y position of the end effector. The y position of the end effector is right here. This is the y position of frame 4 relative to frame 0. Can we write this distance in terms of my joint variables? We can, and we can do it like this. The y position of frame 4 relative to frame 0 is equal to this complete distance, which is A1, minus this distance over here. Now, we can change the order of this equation also to give us an equation for D3. And I see that I just made a mistake here. It's actually not Y04. It's actually Z04 because Z0 is the one that's in this direction. So I'm going to erase my Y here and I'm going to write in a Z instead. So now I've gotten 2 of the 3 equations that I need. I still need to come up with an equation that relates D1. If we go back up to our kinematic diagram, here's D1. If you see the direction of D1, you see that when we look at this manipulator from the side, D1 is invisible to us. So we won't be able to write an equation for D1 from the side view. Instead, we're going to have to look at this manipulator again from the top view in order to get an equation for D1. Let's do that now. When we look at this manipulator from the top view, we're going to put our eye up here and we're going to look down, straight down onto this manipulator. And when we do that, we're going to think about what this manipulator will look like when we look down from the top. Here's what it will look like. First, we'll see joint number 1, and the axes that we'll see on that will be Z1 pointing in that direction, and we're going to see X1 pointing off to the left. Y1 will be invisible to us. However, we'll still be able to see some of the axes from the 0 frame. For example, we'll be able to see X0 pointing off to the right, and we'll be able to see Y0 pointing in the same direction as Z1. Next, we'll have the link leading to joint number 2. And we'll see some of the axes from joint number 2. We'll see Z2, and we'll be able to see X2. But we won't be able to see Y2. Finally, we have joint number 3 over here. And we have the axes that we can see from joint number 3, which will be Y3 pointing to the right and X3. But Z3 will be invisible. We also won't be able to see the end effector, but we will be able to see some of the end effector axes. We'll be able to see y4 pointing in the same direction as y3, and we'll be able to see x4 pointing in the same direction as x3. Now finally, I need to write in my link lengths and joint variables. Over here we have A2 plus D1 being the distance between the origin of frame 1 and the origin of frame 2, as we can see over here. The distance between the origin of frame 2 and the origin of frame 3 will then be equal to A3 plus D2. Remember that what we're trying to do is we're trying to write another equation where we relate the value D1, which we weren't able to see in the last view, and relate that to the location of the end effector. So how could we do that? D1 is in the expression that relates the vertical distance here between the origin of frame 0 and the origin of frame 2. In terms of the location of our end effector, which value, x, y, or z, does that represent? Well, y0 is the one that is pointing in this direction. So this distance here is equal to the y position of frame 4 relative to frame 0. So I can write an equation like this. The y position of frame 4 relative to frame 0 is equal to this complete distance, A2 plus D1. I can then rearrange this equation to say that D1 is equal to y04 minus A2. And that gives me my third equation. So I now have three equations and three unknowns, x, y, and z locations of the end effector that I can use to calculate the joint variables to get my end effector to a specified x, y, z location. I did the Cartesian manipulator derivation for you first because the Cartesian manipulator derivation is the easiest one. In general, the more prismatic joints that you have in your manipulator, the easier it is to derive the inverse kinematics. And the more revolute joints you have, the more difficult it is to derive the equations. In the next video, I'm going to show you an example with a manipulator that has some revolute joints as well.